They know me by name, they have my order. Last semester I went at the same exact time as I did. I use my points as bucket. I only use my points as bucket. I don't go anywhere else. I've gone to you, they don't give me events. I'm so nervous. Literally being there, I've already. I heard it's a lab. Where?
Okay, welcome back. Goal for today was submitting project 3, and let me mute myself. There we go. Is anyone still working on project 3? What's going on? Yep. Okay. Any questions so far about doing the work? Should be questions. That's what I would think. I would have so many questions, but that's just me. I've been doing this a while. Then quiz 4. That one, I don't know why quiz 4 is there. It should be after homework 4. But next week we'll start working on homework, module 4. Now I'm looking at the schedule. I need to reorganize where quiz 4 is happening. Probably homework and project 4 need to push back some. And we're coming into the final stretch, the last few things that we're trying to do for the semester. Whether we're ready or not, it's happening. We're going. It has been very fast, right? This semester? Each day feels like it takes a long time, but the semester is just gone. Yeah. But here we are. All right, so let me take a minute and check in on project 3 work. And if it's really fine, then we can jump into module 4, taking a look at those kind of concepts, or even start with first problem. On Friday, we're going to take the afternoon off. It's Halloween day. I'm out of town anyway. It's been short but also long semester. We can take the day off. We'll be all right. So Friday, just no class, no requirements, nothing's due. So it's a good time to take a break anyway. So I'm going to go around, check in on project 3, and then we'll figure out where, do we want to look at it more or do something else? Was there any of the questions at the end? Were you able to Yeah, so rather than like hypothetical, this is what you could do, just show here it is, yeah, some options. Okay. So it can be anything, but okay, all right, so okay, yeah, that's what I'm checking. All right, so this is one thing, like, um, this last question, it's asking like what other calculations you can compare. It's not a hypothetical. It's not like, oh, we could look at Coriolis effect if we wanted. It's like, no, show me. If you're going to calculate something, if you're going to say you can do 12 different things, you just subscribe to a lot of work of just like, now you need to calculate 12 different values. But the idea is not a hypothetical, what could you do? It's like, specifically, what did you do? How are you comparing these somehow that way? And I ask it this way, like to give you a little bit of practice, like in your career, or when someone asks you like, hey, you're the engineer, what else can we do? They're not asking for like hypothetical, like, oh, we could look at energy, we could look at momentum. They want like, when you do that, what is the difference? Like if you have 10 different ways of doing something that are all the same, you can pick one, do that, and move from there. And again, this is meant to give us some practice of like how to be engineers. So it's not a gotcha question. You can always resubmit. Like if you did the work and you listed maybe 10 different ways of doing something, you can pick one and resubmit that way. That's the main thing. So last time we looked at like actually plotting. So we looked at tension, comparing linear and nonlinear, like what is the tension in the cord. You could also, like if you don't want to code and you don't want to troubleshoot things, we have information, like the things that we plotted, those are all real values that we grabbed from these plots. So you could take, like if you need acceleration, you could grab the data from this plot, like what's the max, what's the min, and make like a table of comparison values. So it doesn't have to be a plot. Plots are nice because they show a lot of information, but if you want to do like a table of some calculations, that's okay too. That was like general advice that I thought would help.
Yeah, I just uploaded it just to make sure something we came up with.
Yeah, that go.
All right, I mean, see the difference here.
The project, I don't think we have too many questions. The project seemed pretty straightforward.
Like I answered most of the questions.
Okay, yeah.
I should be good to go.
And you have like quantified answers for specific measurable statements.
honestly, one real life example of like breaking ball.
What's the other thing? Oh, yeah, that's me. Yeah.
Instead of.
I would not say it's too early or whatever, but
Once it becomes a smooth
it always does.
we have
Oh.
if I convert that into worst case would be
I thought you were talking about the second one.
non-zero values next semester.
Yeah.
That way,
These were my like only options for everything.
it's been nearly as much.
Or no, this is probably yeah, this is
And then have to do it is to see if it's possible.
oh, you took that.
Don't take it next semester.
Oh, we have that class. Okay. I'm looking because my classes with people, so I'm just my options were so limited. Yeah, I just had somebody like that. That's a good bit. I honestly think really want to go this semester.
Is it like, I mean, linear assumes that the side of the it can only be more than
She made a functional class.
But I think any error that's like in the non-linear one,
We factored this class in.
any error due to like us not calculating something else, like it's also in the linear one too, I guess. Would that really?
Well, you can't do it next semester.
Oh,
So we can say with her, this year.
That's why.
you're not wrong.
How is this for her? Well, maybe she's like too long. Well, too late. She says the other one is worse than her.
There's a whole other complicated factor.
She said it like 3 times.
Can you quantify that? Yeah, yeah, you can quantify how much you can without yeah. Yeah, and that's a whole other field of computation. So main things like
Yeah, so there is some it's smaller than
I'm sure I can switch it around.
Is that where the
No, maybe I'll switch it around.
Okay, that's where the most.
This sounds awful.
Let's see if I'm still logged in. All right, so we were just having to talk about like which answer is more accurate, the linear blue curve or the red nonlinear curve. And so one thought is that the linear is, because we're saying sine theta is theta, that introduces some error right here. It introduces, like, there's got to be something wrong with that statement. It's not always really wrong. Sometimes it's just a little bit wrong, but so that introduces error. So for a large, like if we have a large angle, then our blue curve, our blue linear curve does have error because sine of theta is not the right value. But what about when we do have like a small angle? So 30 was my rough number. I don't know if you also figured out a number for yourself, but definitely 10 is a small, 10 degrees is a small angle. And here, it looks like no difference. But if I plot, put a fancy delta. But if I plot here, the error is not zero. Like it looks like the same, but it starts off at 0 and then keeps growing. Should we still say that nonlinear is our like best estimate? Or is there something that the linear is doing better here? Like where's this error coming from? Is it error in our nonlinear or error in the linear? Because this is part of that question of like which one's more accurate. It's like, well, all we can do is compare them, and there is an error between them. So which one are we saying is like, this is my best estimate for what's going on? Should we always use nonlinear because it works for large angle? Yeah.
I think the linear is more for like simple estimation. And
Okay.
getting like a factor of safety in there. If you really want to model emotionally,
Nonlinear is better. So you think this motion, you think the error in this motion of like our delta theta is because there's a nonlinear, like linear has error, but nonlinear is right. Maybe?
One of like averages or estimation of linear, because it's everything sort of stays on the same lines. Like the troughs of the crust are the same distance, get easy with like wave height or something.
Yeah.
But if you want to look at like the actual shape and how it changes over the time, you can pull like it's non-linear, because we see very clearly in the non-linear that it's not always the same amplitude each time, between each second.
Okay. Oh, the amplitude changes for nonlinear? Or?
Well, it looked like it was like going down a little and coming up.
Oh, sorry, on this next one, right?
Yeah.
Oh, okay. So this one is looking at linear minus nonlinear, of just like saying error is some difference in theta. Yeah, so it's not that the nonlinear has a growing. If the amplitude grows, then we know it's got to be wrong, because then we're getting energy for free, but we can't. We need conservation of energy, minimum. So this is saying that like over time we keep increasing how much the difference between linear and nonlinear. And I mean the answer can get complicated. Like you can get deep in the weeds of like numerical methods and how you integrate things. But there is, because we're using a computer to solve this problem, computers always introduce a little bit of error. Like anytime you say like, here's a bunch of numbers, do something with those numbers for me, like give me an answer. Even just storing a number on a computer introduces some error. So for a small angle, the solution that it's a cosine of omega t, that's an exact solution. There's no real question about it. Like maybe we're losing 10 to the negative 15 degrees on there because we're still saying sine theta is theta, but it is exact. It's so numerical methods do introduce some error. So if it's a small angle and they look like they're the same, then the difference you're seeing is due to computer error more so than like our model didn't work right or something. But for large angles, yeah, we're probably justified in saying like sine theta is not theta, and therefore all that error came from that approximation as you keep getting larger and larger angles. Yeah, and there we would see it as we go to like 60 degrees. Now we start seeing delta thetas of like 20 to 40 degrees at each time step. And that's because there's an actual, like, something different is happening. Like, the physics are a little different than just a small angle approximation. Cool. That was the only things that came up, at least so far. Is there anything else we're working on? Cool. So module 4 is our last like assigned module. After this, it'll be independent projects that everyone works on. So this is the last, this is it. As far as like the required things that I'm telling you, this is what's important. We ready to try our first module 4 problem? I think you're ready for this one, even if you haven't done like reading, like haven't studied the material yet. We're in deep space on a 10,000 kilogram spaceship. The spaceship thruster produces 100 newtons of thrust, anti-aligned with the velocity. How long should the thruster fire to bring the spaceship to rest in absolute space? What do you think? How do you start? What do you even start with this? Free body diagram? Love it. Free body diagram? Always into that. All right, what does it look like? This is kind of the standard way that we have been approaching these kind of problems. So velocity is this way, thruster is that way. Yeah, so if they're aligned, it would speed it up. So anti-aligned is slow it down. No gravity because it says deep space. Yes. Usually that's kind of like the indication. So I saw arrows drawn in a few different ways. All right, well, we can call it thrust, like just pointing left. We're in absolute space. Space is like time and space, it's all meaningless, but somewhere. Thrust is pointing that direction. What about MA, like our mass times acceleration? Also same direction? Opposite direction? So here, again, kinetic diagram is the only thing kinetic diagram cares about is what is your frame of reference? So are you saying to the left is a positive motion, or is the right a positive motion? So if the left is positive, then your initial velocity would be negative. If the right is positive, then then you'll have a negative acceleration, but positive velocity. Is that, you see what I'm saying there? So we just need like, and this is kind of one of the things about Newtonian mechanics. It's like the assumption is you can always make some kind of reference frame where everything's moving relative to that. And the big assumption is that there is some fixed, that all these like local coordinate frames are always in relation to some global, like universal fixed point that we can always find. So far we haven't really found that. Like science hasn't discovered like origin 0, not like mile marker 0 in Florida or something. There's no. So if I come in here and say like, this is X, that's Y, I want to call this FT, then MA is anti-align, like we have positive velocity, negative acceleration, something like that. All right, what do you think? Try it however you want. I think you can come up with an answer. So I want to know like, what's your next step from here? So what's coming up next?
Oh, that's right.
Okay, and then use like kinematic equation. Okay, yeah. So we can show the constant acceleration. Kinematic is
We're thinking there's equations of motion.
okay.
That seems to be the general progression.
Yeah. Yeah, you can never go wrong with like an equation.
Exactly.
Yeah, so that would be like, what is the, so is that, like, I mean, this was
And then equals F bar.
okay.
That's what we're trying to get to at least.
Yeah. Yeah.
Yeah.
Yeah.
Yeah, so.
Yeah. Is that TG?
No.
Okay.
No, but MA is, yeah, so. Right.
Yeah, so.
And MA should be constant. Okay.
Alright, cool. So this is, I've seen a little bit of this so far. Some of the forces is mass times acceleration. Everything's kind of in line. Like, it's not that we have one-dimensional motion, but all of our forces are along like one axis. So really, we only really care about that 1 degree of freedom. It's like forward and backward sort of acceleration. So I can say a negative ft is ma. And at least this is what I saw so far. It's like getting to that point. All right, now I have acceleration. Acceleration is dv dt, and that's d squared x dt squared. So for constant acceleration, we know like how to solve that equation of motion. We can say like, here's my initial condition, and let me go from there. Or plug it into like kinematic equations, right? Like we can say change in velocity is a times delta t, something like that. Cool. This is something new from this module. So it's going to give us the exact same equation. We're still going to end up with that same result. The only difference is we don't have to think about like what are the kinematic equations, or we don't have to integrate anything. It's just this general idea that like F delta t is a change in momentum. So if I apply a force for a given amount of time, it will change momentum. Kind of makes sense, at least like intuitive, feels right. So let's write out an impulse. So this is impulse. Momentum diagram. These are great for things like there's a change in velocity, like you're going one way and then all of a sudden you hit something and now you have to go a new way, or an explosion, like where no external force was applied but things changed. So a lot of times all we really care about is like what is the impulse applied by that change in momentum. So first we write out like our initial mv0. So initially we're moving to the right. I add to that force of thrust. And really it's like ft delta t, like whatever that force was being applied to our spaceship. And then the final thing that happens is that mvf is 0. This is very similar to like a free body diagram and kinetic diagram, but one question that came up was like, where does momentum go in a kinetic diagram? And kinetic diagrams don't care about momentum. It does not matter how fast you're moving in, at least Newtonian mechanics. Relativity, that's a different story, the time and space connection. But here in deep space, 100 Newton thrust, not moving that fast, we can draw it this way. So this is where we can actually incorporate like what are changes in momentum. So now I have mv0 minus ft delta t equals 0. Let's leave it as a So when I first like set up that kinematic equation, I said Vf minus V0 is A delta T. now I have F over M delta t is Vf minus V0. What's F over M? What's that? It's acceleration, right? So we ended up with the same, like A delta t equals Vf minus that V0. Kind of neat. And I got to there without, all I did was, like, I'm definitely dealing with vectors. Like, it's not like, oh, it's so easy with impulse momentum, but I didn't have to do any calculus, because this whole idea of like impulse being equal to a change in momentum, the calculus is already done for you. Like, you already have one step done. It'll always give you some like time and speed connection, like how fast are things changing speed. All right, cool. Then question is, what is delta t? How long does the thruster need to act? $5,000 seconds? What do we think? Same. What was the impulse applied by this rocket? Like, let's say we wanted to increase the thrust. How much can we decrease that time by? Up to acceleration. What do you mean acceleration of light?
So we can accelerate up till the speed of light, at which point we can't accelerate anymore.
Well, in this case, we're trying to slow down. So here, yeah, as long as we don't like speed backwards to the speed of light, then we're okay. We can try, like, you can apply a force as long as you want. It's just the physics change along the way. You can't, same as like saying a small angle is sine of theta. Newtonian physics works really well as long as you're less than 90% of the speed of light. I think 80% is a solid number. Yeah, what is this number? Like, how big is this? That's our impulse, our thrust times delta t. So in order to bring this thing to a stop, we needed 500,000 Newton seconds, or like what is that? 0.5 meganewton seconds. So we could apply a force of 0.5 meganewton for 1 second and just send everybody flying through the window, because that's a large, yeah, changing your speed from 50 to 0 in 1 second is probably not a great idea. It's a lot of G's to go through. But that number is not going to change. Like, in order to bring this thing to a stop, no matter how you do it, whether you bring it gently or abruptly, we need 500,000 Newton seconds. And again, kind of a nice way to like approach different engineering problems. Cool. I think that's a good start. And we'll take Friday off, celebrate Halloween, be back on Monday. Cool. Anything else for today? I didn't want to jump into something new with 5 minutes, since we've gone like 5 to 10 minutes over once or twice. 5 minutes early, we're good. Cool. Thanks a lot.